All right, today we're looking at DiffRatio, training one-step diffusion models without teacher supervision. This is a big one coming from researchers at Bosch, UCL, Cambridge Imperial College, and the Max Planck Institute.
And the headline here is just, it's all about speed. They're getting these incredible high-fidelity images. We're talking ImageNet 522 by 512 with an FID of 1.41 in a single step. NFE equals 1.
And the kicker, the big claim, is they're doing it without that standard teacher supervision loop you see everywhere in distillation. So no more calculating a teacher score than a student score and trying to get them to match up.
Exactly. They just throw out that whole idea of score distillation, which, is basically subtracting two noisy estimates. Instead, they use something called density ratio estimation. They've cleverly turned a score matching problem into a classification problem,
which gets rid of that bias accumulation you see when you're subtracting noisy gradients. And it means a smaller auxiliary network, I think they said half the size, and it's beating most of the big teacher-supervised methods on CIFAR-10 and ImageNet.
That's the 1-minute summary. Now let's get into the math.
Let's do it. So anyone working in generative AI right now knows this pain. Diffusion models, quality-wise, are incredible, but the inference speed, it's a killer.
Oh, yeah.
You're running that UNet, 50, 100, maybe even 1,000 times for just one image.
It's the NFE bottleneck, the number of function evaluations. And if you want these models in, real-time apps or on your phone, you need that number to be 1. It has to be one-shot generation.
So the go-to method for that has been distillation. Take your big, slow teacher model, train a smaller, faster student model to just jump to the end result in one step. And for a while, the king of that has been VSD variational score distillation.
Right.
But this paper's whole premise is that VSD has, a kind of fundamental flaw.
Flaw might be a strong word, but yeah, let's call it a statistical inefficiency. It all boils down to what they call the two-source bias.
Okay, walk me through that.
So with VSD, you're trying to figure out the right gradient to update your student model. To do that, you ask the big pre-trained teacher model, hey, what's your score estimate? Where's the noise pointing?
Okay.
Then you ask your student the same question. And then you subtract the student's answer from the teacher's answer to get your update direction.
Which just sounds logical, right? You want the student to act like the teacher, so you minimize the difference between them.
It sounds perfectly logical, but statistically, it's a mess. Because the teacher and the student are both outputting estimates. They both have their own error, their own variance. They're both noisy.
And when you subtract two noisy things,
you don't get a clean signal. You sum the variances. You're actually making the signal you're training on noisier than either of the individual parts.
Right. You're compounding the error.
Exactly. The paper has this great analogy. Imagine you want to measure the distance between two moving cars on a highway.
Okay, car A and car B.
The VSD approach is like asking one person to guess the GPS coordinates of car A, and then asking a different person to guess the GPS coordinates of car B. Then you subtract the coordinates.
And if they're both off by a little bit?
Your final distance could be wildly wrong. If one guy is off by 5 meters north and the other is off by 5 meters south, your distance is off by 10.
What all you really wanted was the relative distance between them. You didn't care about the absolute coordinates at all.
You just wanted a tape measure between the bumpers. And that's what DiffRatio sets out to do. It stops trying to guess the absolute score of the teacher and the student separately. Instead, it directly estimates the ratio of their densities.
So it's the laser rangefinder instead of the two guys with GPS.
That's the perfect way to think about it, yes.
Okay, so how do you build that mathematical laser rangefinder? Because we don't actually know the true probability distributions for these, incredibly complex images. You can't just write down a formula for image.
And this is where they pull out a really, really nice trick from the statistics literature. They use Bayes' rule to flip the problem on its head. They turn a score estimation problem into a binary classification problem.
A classifier trick.
That's the one. So if you look at the math, the gradient we want is basically log Q minus log P, the student score minus the teacher's.
Right.
But, with basic log rules, that's mathematically identical to the gradient of the log of the fraction, Q divided by P. And that fraction is the density ratio.
Okay, so we need to find that ratio, Q over P. How?
Well, it turns out if you just train a simple binary classifier to distinguish between samples from Q, the generated data, and samples from P, the real data, the optimal classifier implicitly learns that exact ratio for you.
So you just train a little network to play real or fake.
Exactly. If your classifier outputs C of X, which is the probabilities that an image X is real, then the density ratio is simply 1 minus C of X divided by C of X. You can get the ratio just from how confident your classifier is.
That feels so much cleaner because classification is, it's a much more constrained problem than score regression.
It is. It's much more stable. You're not predicting some high-dimensional vector that can point anywhere. You're just predicting a single number between 0 and 1.
And this means you can just drop all the heavy machinery that VSD requires.
That's the big efficiency win. In VSD, you have to keep a frozen copy of the massive teacher UNet in memory, plus your student UNet. With DiffRatio, you replace that teacher score network with this density ratio estimator, which is just a classifier.
And I saw in the paper they build this classifier using just the encoder half of the UNet.
Right, because you don't need to generate a new image, you just need a single probability out. So you chop off the whole decoder, you've instantly cut your auxiliary memory cost in half.
So lower VRAM, faster training.
And a cleaner gradient signal. It's a win-win-win.
Now, I'm always a little bit skeptical when a paper says their math is cleaner. Does it actually hold up in a controlled test? I was really drawn to that 2D toy experiment they did.
I love a good toy experiment. It strips away all the, deep learning magic and just shows you the raw vector fields.
So they set up this mixture of Gaussians, 40 blobs of data in a pattern, and tried to learn it with both VSD and DiffRatio.
And the key is, because it's just 2D, they can calculate the actual ground truth. They know exactly what the gradient vector should look like at every point.
The results in Figure 2 were not flattering for VSD.
No, they really weren't. They measured two things: L2 error, so how far off the magnitude is, and cosine similarity, which is whether it's pointing in the right direction.
And for DiffRatio, the L2 error just drops as the noise level goes down. It gets more and more accurate.
Meanwhile, VSD's error either stays high or actually gets worse as you get closer to the data. It's just confirmation of that variance accumulation we talked about.
But the cosine similarity chart was the real shocker for me.
Oh, absolutely. That chart shows if your gradient is even pointing the right way. DiffRatio is sitting almost perfectly at 1.0. It's like a perfect compass needle pointing true north. It knows exactly where to go.
And VSD.
It can't even break 0.7. It's wandering. It's like a compass that's constantly jittering 30 or 40 degrees off course.
So you're getting a much, much higher fidelity navigation signal from DiffRatio.
And that's what matters. When you're trying to do this in a single step, you don't have 50 chances to correct your course. You have one shot. That gradient has to be perfect.
Okay, this brings me to a question about the whole setup. We've got a generator and we've got a discriminator, which is the classifier. This is starting to sound suspiciously like a GAN.
It is.
Are we just reinventing the wheel here? Are we back in 2017?
It's a fair question. Structurally, the setup, a generator versus a classifier, is absolutely a GAN. But there's a crucial difference that solves the biggest headache of training GANs.
The mode collapse, the vanishing gradients.
Right. And why does that happen? Because in a high-dimensional space, like images, the manifold of real images and the manifold of fake images almost never overlap. They're disjoint.
Which means the discriminator can find a perfect separating line instantly.
Instantly. It gets a perfect score, the gradient goes to 0, and the generator learns absolutely nothing. Classic GAN failure. But DiffRatio operates on diffused inputs.
So we're adding Gaussian noise to both the real and the fake images before the classifier ever sees them.
And Gaussian noise has support everywhere. It essentially smears both distributions out so they cover the entire space, which guarantees that they will always overlap.
The noise acts as a bridge between the two manifolds.
Exactly. It keeps the math valid, it keeps the divergences well-behaved, and because we're in this diffusive framework, we can use all these different training objectives that would be totally unstable in a normal GAN.
The paper introduces 3, DFRAL, DJS, and DWAR.
Okay, so DFOIL is diffusive KL divergence.
Yeah, that's kind of the standard, the baseline approach.
Then there's DJS, diffusive Jensen-Shannon.
That one's symmetric, but
Okay.
basically tries to minimize the chance that the generated data is classified as fake. And in their experiments, this one was actually the top performer. It seemed to give the best balance.
And finally, DRARM, diffusive realism maximization. This one just maximizes the probability of being classified as real. It's a bit like the old non-saturating GAN loss. It can give you really sharp images, but sometimes at the cost of a little diversity.
And what's really cool is you can just swap these out, right? The architecture stays the same.
Totally. You just change one line in your loss function. You can tune the flavor of your generation without re-engineering the whole thing.
Okay, I want to pivot to the part of the paper that, well, it caused a bit of a stir when we were prepping. The title is Without Teacher Supervision.
Ah, yes. The clickbait charge.
But then you get to section 3.4, and they explicitly say they initialize the student model with the teacher's weights. So Is it fair to say no teacher if you're basically cloning its brain at the very beginning?
I think it is, but you have to be very precise about what supervision means. In the world of VSD, supervision means an active runtime dependency. During every single training step, you have to query the frozen teacher network to get its scores.
Which is computationally expensive.
Very. With DiffRatio, you do a one-time copy-paste of the weights at the start. You just are the teacher. You never ask it for anything ever again. So the training process itself is unsupervised by a teacher.
Okay, I can buy that distinction. But it begs the question, why is that initialization necessary at all? Why can't we just train one of these one-step models from scratch?
They tried it. They ran the experiment, initializing the generator with just random noise.
And what happened?
Total failure. Complete mode collapse. The model just spits out gray noise or converges on a single, blurry, average-looking image.
Why, though? If the loss function is mathematically sound, why can't it learn?
The authors call it the feature space hypothesis. The idea is that if your generator starts from nothing, the classification tag is just too easy. The classifier wins instantly, gradient vanishes, game over. But if you start with the teacher's weights, the generator already has a rich vocabulary of visual features.
It already knows what edges and textures and object parts look like.
Exactly. It might not know how to assemble a perfect cat in one go, but it knows the building blocks. And they did this really brilliant ablation study to prove it. The cross-class initialization.
This was my favorite part. They took a teacher model that was trained on CIFAR-10.
Right, which has classes like beavers, motorcycles, orchids.
And they used that to initialize a student that they then trained on CIFAR-10, which has frogs, airplanes, cars, completely different non-overlapping classes.
So the teacher has literally never seen a frog. He has no concept of what a frog is. And yet, when they used those weights, the training was perfectly stable. No mode collapse.
That's incredible. So it's not the high-level knowledge of this is a frog that matters. It's the low-level structural knowledge of this is how you render fur or this is what a shadow looks like.
Precisely. It's the feature extractors that you're inheriting. Once you have that stable feature space, the one-step training is just about aligning those features correctly.
So we have the theory, the architecture, the initialization trick. Let's get to the bottom line. How does it actually perform?
The numbers are really strong. On CIFAR-10, with that GJS objective we talked about, they hit an FID of 2.39.
FID, Frischette inception distance. Lower is better. 2.39 is pretty good.
It's top tier. It's significantly better than VSD, and it's right up there with the best, most complex distillation methods out there.
What about when they scale it up? ImageNet 64 by 64.
An FID of 1.54. That beats the VSD baselines, and it matches state-of-the-art methods like CETA. But here's the thing. CETA needs you to first generate this massive synthetic data set to train on. DiffRatio is simpler. It trains directly on the real data.
A much cleaner pipeline. And then the big one, ImageNet 512 by 512.
FID 1.41. Now, to be fair, they used a beast of an architecture for this, the EDM2M unit. But still, getting an FID that low in a single sampling step, that's a huge achievement.
And doing it all with an auxiliary network that's half the size of what you'd normally need.
That efficiency matters. I mean, it translates directly to cost and accessibility. Having the memory for your training objective, that could be the difference between being able to run an experiment or not for a lot of labs.
It really feels like this paper is building a bridge between two worlds that have been kind of separate for a while. You had the score matching camp and you had the GAN camp.
It really is a unification. It's using the stable mathematical framework of diffusion, the noising, the score theory, but it's solving the optimization problem using the mechanism of a GAN with a classifier. It's the stability of diffusion with the efficiency of GANs.
So here's the big question then. If this density ratio approach is so much cleaner, could it go beyond just distillation? Could you train the base models this way from the start?
That is the provocative thought, isn't it? If that little 2D experiment proved that estimating the ratio is mathematically superior to subtracting noisy scores, why are we still subtracting noisy scores to train our foundation models?
Right. Why do it at all?
You can imagine a future where we train these massive models from scratch using a density ratio objective. It would take some re-architecting for sure, but if the gradient is fundamentally cleaner, the training should be faster and the results should be better.
Turns out the best way to measure the distance between two cars isn't to ask two people to guess their coordinates.
Just use the laser rangefinder.
We'll leave it there. This has been a look at DiffRatio. For the ML engineers listening, definitely check out the appendix on the classifier architecture. There are some neat implementation details there. We'll catch you on the next paper.